Okay, this is a continuation of chapter 16. So we had gone over what factors affect the rate of solution formation. We've gone over factors that affect the solubility, right? One of the things that we said the solubility was based on, for gases anyways, was based on pressures. So pressures can change the solubility of a gas. Higher pressure, higher solubility of a gas. That was known as Henry's law. That was the last thing that we had gone over. The rest of chapter 16 involves numbers, okay? It involves actually calculating concentrations. So the first thing we're going to get into here is concentrations. Again, since we're getting into numbers, make sure that you have available not only your paper and pencil that you're writing all this down on, but access to a calculator, right? Because it's really kind of pointless to just stare at a bunch of numbers unless you try them yourself. When we talk about concentration, right? Concentration is just the amount that's being dissolved, the amount of solute that's dissolved, and it always has to be in a certain amount of solvent. Right? And there's different ways of stating concentration. You could do it qualitatively, right? Qualitatively refers to something that doesn't involve numbers. Like for instance, if we had not very much solute in our solvent, then we would say that's a low concentration. Another word for that is dilute. If we had a lot of solute dissolved in our solvent, then we would have a high concentration. We call that concentrated. Right? So dilute and concentrated are words that we can use to just give a general idea of what the concentration is, but it's not an exact number. What's dilute for one solution may not be the same as dilute for another solution, so those are not really great terms to use on a regular basis. Right? It's kind of like if you wanted to go ahead and make a solution at your house. For instance, let's say you bought a packet of Kool-Aid. Now the packet of Kool-Aid doesn't say on the back, oh, make a concentrated solution of this or make a dilute solution of this. It simply tells you the amounts. It says pour this packet in and put so much water in with it, okay, and stir. So they're telling you an exact concentration they want you to make of it. Now you could change that, right? You could put less water in and make it more concentrated, or you could put more water than the packet says and you could make it more dilute, right? But there's a certain concentration they're referring to there. So there are quantitative ways of stating the concentration. That's the thing that we're going to spend most of our time on here. So one of the ways that we can describe the concentration of a solution quantitatively is by a percentage. Right? For instance, we could do a percent by volume. You notice that the abbreviation is the percent sign and then V over V. So percent by volume is the volume of the solute divided by the volume of the solution times 100. Okay, to turn it into a percentage. So these are volumes. So this is when we're talking about things like liters or milliliters or cubic centimeters, right? Those are volume units. So this would be really good if we're doing, like, let's say liquids, right? Because if you're talking about liquids, usually you measure liquids in volume. You can measure the mass of a liquid, but we don't do that very often. We usually measure the volume of it, so this makes more sense. So let's do a practice problem. If 10 milliliters of pure acetone is diluted with water to a total solution volume of 200 milliliters, what is the percent by volume of acetone in the solution? Okay, so according to this, we kind of read through it really quickly. We see that they're taking acetone and they're dissolving it in water. So acetone must be the solute, water must be the solvent. Okay, so they gave us the volume of the solute. They said that it's 10 milliliters of pure acetone, right? So 10 milliliters of pure acetone. that must be the volume of the solute. And then they tell us that we have a total solution volume of 200 milliliters. So that must be the volume of the entire solution. By the way, the abbreviation for solution is SOLN. So I'll use that sometimes. And so then they're looking for, obviously, what is the percent by volume. So we're going to use this setup that we just talked about right here. And we're simply just going to fill in the numbers that we have in the problem. So the percent by volume is the volume of the solute, so that's 10 milliliters, divided by the total volume of the entire solution, which is 200 milliliters, times 100. So 10 divided by 200 times 100. Right? If you do that on your calculator, you should get 5. And so this tells us that we had just made a 5% solution of acetone in water. Okay. So does that sound like it's really concentrated, or does that sound like it's really dilute? Well, it's only 5%. So that sounds like a pretty dilute solution of acetone in water. All right. Now, there's also percent by mass. Okay, percent by mass is just like percent by volume, but instead of using volumes, we're using masses. So we're using things like grams or kilograms or something like that. Okay, so it's mass of solute divided by mass of solution times 100. So it's just like doing it with volumes. Right? You have 1, the solute, over the total, which is the solution, times 100. You just have to make sure that this is all in grams. So let me give you an example of a percent by mass problem. But instead of making it really simple like the last one was, let's put a little twist in it. So this practice problem says, calculate the grams of solute required to make 250 milliliters of a 0.1% by mass MgSO4, that's magnesium sulfate solution. All right, so we've got a few things that we need to figure out here before we can even attempt to start this problem. First off, I need to know what is the solute, right? So what is being dissolved? So in this, it says that we're making a solution of MgSO4. So the solute is what we're trying to dissolve. So the MgSO4 must be the solute. Now, do they tell me the mass of the solute? Did they tell me the grams of MgSO4? Nope. There's no grams of MgSO4 here. So I don't know what the mass of the solute is. In fact, you can see in the problem it says, calculate the grams of solute. So they're asking, what is this? I don't know what this is. Okay? So this is going to be our unknown here in this equation. Now, they do tell us that it's 0.1% by mass. So this time they're actually giving us this side of the equation. They're telling us what this is. So if we don't know the mass of the solute, we do know the percentage. So the other thing that we're going to need to know is what's the mass of the solution. But here's the tricky part about this. They told us that we have 250 milliliters of the solution. Now, milliliters is not mass. So we can't just take 250 and put it in for mass of solution. It wouldn't necessarily work. So the question is, how do we get milliliters into grams? Now, I know what you're thinking. I know exactly what you're thinking, right? You're thinking, okay, if I go back to what we just learned in the last few chapters, we always have to change things into moles. So this is going to be one of those mole problems. And that's not true, okay? Milliliters to grams has nothing to do with moles. I want you to think about it. What do we know that has mass and volume? Because 250 milliliters is a volume. What has mass and volume in it? Something we learned a long time ago in this class. Mass and volume are used to calculate density. So density is what we would need to hear here to actually change milliliters into grams. We would need to know what's the density of this solution. Now, they don't tell us that in this problem. So it seems like we're at an impasse. We can't do this problem, but we can. We need to make a couple of assumptions, right? Simple assumptions, assumptions that aren't really hard to do. One of them is, what are we dissolving the MgSO4 in? It doesn't say that. So one of the assumptions we can always make in these problems is, if it doesn't tell you what the solvent is, assume it's water. So I'm going to assume that the solvent in this case, the MgSO4, is being dissolved in water. The second assumption we're going to make is, what's the density of this solution going to be? Well, you can see that it's only 0.1%. 0.1%. Now, does that sound like it's very concentrated to you? Does that sound like a lot of solute? No, it sounds like a very, very small amount of solvent or solute. So that means this is mostly solvent, right? This is like 99.9% water. Now, we know what the density of water is. The density of water is the easiest thing in the world to memorize. The density of water is 1 gram per milliliter is the density of water. So how does that help us? Well, let's think this through now. If I have 250 milliliters of a solution that's mostly water, and I know that there's 1 gram for every milliliter, well then 250 milliliters is basically 250 grams. Now, you've gotten all the way through to that point and you're like, wait a minute, so we still could have used the 250? You're right, we did, but we didn't know that until we thought it through. We can't just randomly take the 250 milliliters and put that in for a mass. We had to make sure how many grams that was. And it turns out that it's 250 grams also, because water is always 1 gram per milliliter. All right, so let's put this together now. We have 250 grams of solution. We have 0.1% as the percentage. We don't know what the mass of the solute is, so let's set this up. All right, so this is 0.1%, that's the percentage. This is 250 grams, that's the milliliters of solution, or milliliters, that's grams, the mass of solution, sorry. On the top is the mass of the solute, which I don't know, so I just abbreviated it M. You can call it whatever you want to. You can call it X, you can call it whatever, but I just called it M because it's the mass of solute that we need to find. And this is still multiplied by 100. So we still multiply by 100 here. So here's what I want you to do. I want you to take a couple of moments, pause this video. I want you to solve for M. Now remember, the units are all going to work themselves out, so don't worry about what the units are. So you've got 0.1 on the left. Don't worry about the percent MM, that's just the unit. That equals M, that's my unknown, over 250. Don't worry about the G, that's just the unit, times 100. So it's 0.1 equals M over 250 times 100. Well, that's a pretty simple algebra problem. And I want you to take a couple of moments, pause this video, and solve for M and see what you get. Okay. So you've already solved this, right? You've already gone through and figured out what M is. So the first thing I would have done to solve this is I would have taken that 100 that's over there. If you want to get rid of that 100, you're going to have to divide both sides by 100. So I divided both sides by 100, and then it turns into a cross multiplication. So I took this 100 here, and I divided each side by 100. Right? That's where I got that from. So then it's 0.001 equals M over 250. Now I can cross multiply. So M equals 0.25. This is a mass, so it's going to be in grams. Okay. So here's the deal with percent problems. Percent problems, the equation for them is pretty simple. It's solute over solution times 100. So it's either percent by mass, so it's mass solute over mass of solution times 100, or it's percent by volume, which is volume of solute over volume of solution times 100, right? So they're pretty similar, and aside from occasionally having to make some assumptions like in this problem, there wasn't much to it. But I'll tell you right now, the percentages are not the way that we generally are going to talk about concentrations. It happens, you need to be prepared for it, right? But we actually don't use that very often. The unit that we use the most often in chemistry to talk about the concentration of a solution is called the molarity of the solution, okay? Molarity is abbreviated capital M. It is really important that you use capital M to abbreviate for molarity. And molarity is moles of solute divided by liters of solution. Notice a couple things. There's no multiply by 100 because this is not a percent, okay? Second of all, it's moles of solute on top, and it's liters, not just any volume, it's exactly liters of the solution on the bottom. So moles over liters is what molarity is. All right, this is the most used unit of concentration in all of chemistry. This is what we will be using 99% of the way the rest of the year, okay, all the way to the end of this class. When you see this, let's say, it says that we have a 3M solution. The M stands for molarity, so we say that's a 3 molar solution. What does that really mean? Well, look at our equation that we had up at the top here. Molar, right, is moles per liter. So if I say 3 molar, then I mean that there is 3 moles of solute in every liter of solution. That's what that means, okay? Now, why is that more useful than like a percentage? Because moles works for any kind of substance. It doesn't have to be something that we measured in volume. It doesn't have to be something we measured in mass. It could be a solid, a liquid, a gas. Everything can be measured in moles. That's why this is usually used most often. What it does require, however, is that you can change things into moles, right? If you don't have moles, you're going to have to convert into moles, which is why one reason why we learned how to do that in chapters 10 and 12. Okay? So again, let's do a practice problem here and see how this is a typical molarity problem. It says we can make a saline solution, which is really just a dilute salt solution. It contains 0.9 grams of NaCl per 100 milliliters of solution. What's the molarity? All right, so we're solving for molarity. We know that molarity is moles over liters. Moles of solute divided by liters of solution. Do they tell us, first of all, let's figure out what the solute is, right? What's being dissolved? Well, it's pretty obvious. It's the salt, right? The salt's being dissolved. What's it being dissolved into? It doesn't say. So once again, what do we assume? We assume the salt's being dissolved into water. So this is a salt water solution. But they don't tell us the moles of salt. They tell us the grams of salt. Right? So we have to change the grams of salt into moles if we're going to be able to use this in our equation from above. So that's our first job. How do we change grams into moles? Well, remember, you need a periodic table for this. If you did not get one out, make sure you get one out so you can follow along. Again, it doesn't help for you to just stare at the numbers that I come up with if you don't know where they came from. So make sure that you're following along. Get yourself a periodic table out. All right, 0.9 grams of NaCl. We want to change grams into moles for NaCl. All right, so 0.9 grams, that's our given. So we start with our given. We're going to put grams of NaCl on the bottom because grams of NaCl is what we started with. We're going to change that into moles of NaCl. And where does the 58.5 come from? That's the periodic table. I took Na and Cl and added their molar masses together off the periodic table. That's where I got 58.5. So this is telling me that if I take 0.9 divided by 58.5, that tells me how many moles of NaCl that is, and that's 0.015 moles of NaCl. All right, now I have the moles on top. That's one step of the way, right? I figured out how many moles there are, so this is going to be the 0.015. That's going to go on the top. Now I need liters of solution on the bottom, but they gave us milliliters of solution. So how do I go from milliliters to liters? Well, that's just a King Henry problem. That's just a metric problem, right? King Henry died by drinking chocolate milk. I want to change milliliters into liters. So I'm going to go from milli to base, right? Well, how many places is that? 1, 2, 3 places. So if this is 100 milliliters, I'm going to take the decimal point. I'm going to go 1, 2, 3 places over. So how many liters is that? That's only 0.1 liters. All right, so we know that the bottom here is going to be 0.1. So the top is 0.015, the bottom is 0.1. So now I can fill this in and show my work. All right, 0.015 moles of NaCl is the solute. 0.1 liters of solution on the bottom. If I divide 0.015 divided by 0.1, I get 0.15. And so my molarity here is 0.15 molar NaCl solution. Okay? So when we're doing a molarity problem, just remember it's moles of solute divided by liters of solution. So you need to make sure you have moles on top and liters on the bottom when you do this. They're not always going to give you it. They could give you a really simple problem. They could say, this is how many moles of solute you have. This is how many liters of solution you have. What's the molarity? They could be that simple, but they're not going to often do that. Right? So just make sure you have the units correct. All right, one of the things that we want to be able to do is change the concentration of a solution. When we change the concentration of a solution, we're changing either how much solute or how much solvent we're putting into that solution. Like I said earlier, if you were making Kool-Aid and you were making it according to what the packet said, you dump in that little packet of powder and then you pour in the amount of water that it says on the packet. But what if you wanted it to be more concentrated? What if you wanted the flavor to be even stronger than it usually is? Well, you'd put in less water, right? What if you want it to be less concentrated? You'd just put in more water, right? And you'd make it more dilute. So a lot of times in chemistry, for instance, if we're making solutions, we might make a solution and then find out later we need to make it more dilute, right? So what are we going to do? Add water to it. When I buy acid from the chemical company and I need hydrochloric acid, I do not buy every single concentration of hydrochloric acid that I would ever need. I buy one concentration of it, usually a really concentrated version of it, and then I dilute it myself and I add water to it myself when I need it less concentrated for you guys to use in labs. You do the same thing at home when you do laundry. If you use liquid laundry detergent is laundry detergent that's already been dissolved in a little bit of water. But you need it dissolved in a lot of water. So what do? You put it in your washing machine adds all this extra water to it to dilute it. So you've done this before, except that we need to be able to calculate how much. We don't have a little packet or a little bottle that tells us how much to use or how much to dilute it with. Right? So we have to be able to calculate that. So remember, when you dilute something, you're not changing how much solute is in there. You're changing how much solvent it's dissolved in. Okay, so this is the equation that we're going to use to make dilutions with. So molarity equals molarity of the first solution, which is usually the most concentrated solution. That would be the stock solution, we often say, because that's what's in the stock room, like in my back chemical room. So the molarity of the concentrated, the stock solution, times the volume of that solution that needs to be diluted equals the molarity of the diluted solution. So this is the molarity of the solution we want to make. It's usually a lower solution molarity than we started with, times the volume of the diluted solution that we want to make. Okay? So think about this. If we take molarity times volume, molarity is already moles over liters. So if we take moles over liters times liters, we'll just get moles. So what is this equation really telling us? It's telling us that in the end, the moles of the solute that we begin with always equal the moles of the solute at the end of this dilution. What's the only difference here? The only difference is we're changing the amount of water. We're changing the amount of solution total that we're making. That's why the V's are going to be different, and that's going to make the M's, the capital M's, different. But the moles of solute is not changing. I'm not dissolving more or less stuff in it. I'm just changing the amount of water that is dissolved in. So the one thing this doesn't tell you is how much water is it dissolved. So the last thing we would want to do is take V2 minus V1, whatever the difference is in volumes. That's the volume of water that you would need to add to the stock solution to dilute it. All right, so let's try a practice problem. It says, how many milliliters of a stock solution of 4 molar Ki, potassium iodide, would you need to prepare 250 milliliters of 0.76 molar Ki, potassium iodide solution? All right, so let's go through and figure out our knowns. Right? What's important here? So in this problem, I see that I have 3 things that look important. I have this, I have this, and I have this. All right? And we know that we're doing a dilution, right? Because we're taking a concentrated 4 molar solution and we're making it into a less concentration, a diluted concentration of 0.76 molar. So if I'm doing a dilution problem, I know that I'm using this equation, right? Here's my equation that I'm using. And I need to figure out of these 3 things that they gave us, which one of them is M1, which one of them is M2, which one of them is V1, which one of them is V2. All right. Well, we know that the molarity of the concentrated solution is M1. So whatever the most concentrated molarity is, that's M1. So this must be M1, right? So whatever the less concentrated molarity is, that's M2. So this must be M2. So then what is this over here, the milliliters? Is that V1 or is that V2? Well, look what it's attached with. It says it's 250 milliliters of 0.76 Ki. So that must mean this is V2. And then notice what they're asking for. They're asking for milliliters of a stock solution. Well, that's what V1 stands for. So V1 must be the unknown. It's what we're trying to solve for. So this is breaking down the problem so we know how to solve it. So here's our knowns. Right? M1 is 4 molar Ki, M2 is 0.76 molar Ki, and V2 is 250 milliliters. What are we trying to solve for? Trying to solve for V1. Okay. All right. So I want to set this up. So I'm going to take my equation, my M1 times V1 equals M2 times V2, and I'm going to plug in the numbers now. So what's M1? 4. What's V1? I don't know, so I'm going to leave it called V1. What's M2? It's 0.76. What's V2? It's 250. Now, I'm sure there's at least a few of you out there going, wait a minute, don't we have to change 250 milliliters into liters? Because isn't molarity, isn't that deal with liters? And you're partially right. But since we have a V on the left and we have a V on the right, their units would technically cancel each other. So if you left this as 250 milliliters, that's all right, because that just means that V1 will be in milliliters also, and it'll work out. So this is one of those times where you don't have to change it to liters. All right, again, I want you to pause for a moment. I want you to solve for V1 and then come back to this. All right, you've solved for V1, right? So you took 0.76 times 250, and then you had to divide the 4 over, right? And so your final answer is 47.5 milliliters. 47.5 milliliters. So what does that tell us? Since V1 is of the stock solution, that means I need to take 47.5 milliliters of the 4 molar Ki. And what do I have to do to it? Well, I'm diluting it, so I have to add water to it. How much water? Well, they didn't ask us this, but we could figure that out. If you take V2 minus V1, that tells you how much water you'd have to add. So I would have to add 202.5 milliliters of water to that 47.5 milliliters of the original 4 molar solution, and that would dilute it down to 0.76 molar. Okay, that's the whole process of doing a dilution. All right, we're going to end this session here on concentrations because it's usually enough at one time to take in all these concentrations. Make sure you're working on some of those problems in your homework. And then you can go back to the next section here, which is going to talk about colligative properties. Okay?